퍼지 페르미 포텐셜 에너지 그거의 사이 관계를 한 번만 더 설명을 좀 해주실 수 있는지.
좋은 질문이신데 지금 오늘의 주된 주제 중에 하나가 그겁니다. 그래서 그 포텐셜과 그다음에 그 서피스 포텐셜과 일렉트론 페르미 레벨, 쿼지 페르미 레벨인 그 V 사이의 관계에 대해 가지고 설명을 하는 것이 오늘 그 주된 내용이기 때문에 그걸 한번 들어보시고 그 다음에 추가적으로 질문해 주시는 건 좋은 것 같아요. 근데 그게 이제 사실 MOS를 이해하는 데 있어서 상당히 중요한 이야기죠. 그렇습니다. 또 다른 질문 있으신가요? 그러니까 저 학생의 질문은 오늘 수업을 통해서 좀 어느 정도 해결이 될 수 있을 것 같고 다른 학생들 질문 있으신가요? 없으세요? 자, 그러면 시작하도록 하겠습니다. Okay, so in the previous lecture we have introduced 파오사 double integral. So 파오사 integral, the double integral just shows that we can calculate our drain current in terms of double integral for this potential profile and also this electron quasi-Fermi potential. As we know, this inner integral is corresponding to the vertical directional integral, and this outer one corresponding to this electron quasi-Fermi potential. This is related with the channel directional or lateral directional integration. So by performing all kinds of this calculation, so we will find this drain current. Here we have some interesting number 1 over L, and this 1 over L is to compensate our integration over actually starting from 0 to L. We are just integrating a constant ID over length scale from 0 to L. That's the reason why we have here a factor corresponding to 1 over L, so length scale. So if you remember correctly, so at the end of our previous lecture, I tried to show you how difficult to actually calculate this Pausa double integral. It looks beautiful. Formulation looks beautiful. However, in order to calculate this integration for given electron quasi-Fermi potential, we have to integrate some quite complicated integrand, and it was related with the purpose of this kind of thing was related to calculation of inversion charge density. How many, for example, in the case of an MOSFET, how many electrons are there? That was the central question of our calculation shown here. So maybe you can ask me this question. Well, already we have quite much studied the relation between this QS versus surface potential, and even when certain electron quasi-Fermi potential is given, we can calculate this Q sub S. So this is semiconductor or substrate charge in our p-type substrate. We can calculate this quantity quite exactly. Then what was this quite much complicated thing that was related with decomposition of this QS into two parts. One part is inversion charge density, and the other one is depletion charge. So, in the case of our normal operation condition beyond the flat band voltage, actually this QS, when we consider its correct sign, this is a negative quantity. Anyhow, we get some negative charge in our silicon substrate. Then if we decompose it into two parts, there are two different origins of this negative charge. One is this inversion charge, obviously negative, and there is another one corresponding to the imbalance between our negatively charged acceptor dopants and hole density. If they are balanced perfectly, then of course we will have 0. However, if we have some phenomena called as depletion, then we will have negative charge, because usually hole compensate the negative acceptor doping. However, if there is not sufficient number of holes, then they are not fully compensated. That is the origin of this another negative charge. Actually, for relatively low gate bias, this mechanism is more dominant, and if we go to higher and higher bias, gate bias condition, then eventually this one takes the control over entire negative charge density. So we know this one, but point was, yes, for this entire semiconductor charge we can calculate. However, we never tried decompose it into two different parts, for example electron density and hole density. The one we have done in our previous lecture, PAUSA, was actually that one. In this case, from given electric field profile, we try to explicitly calculate inversion charge density, so it does not contain the quantity like this. So we directly calculate inversion charge density. That's the reason why we believe that this calculation is most rigorous and accurate within the restriction of a gradual channel approximation. Of course, we have applied gradual channel approximation, which reduce our two-dimensional Poisson equation into one-dimensional one. But once we accept that the gradual channel approximation, then PAUSA double integral is regarded as the most rigorous one. And now we have finished the study of PAUSA double integral. After that, our lesson is, yes, if we have a good computing resource, then we can calculate this PAUSA double integral. However, unfortunately, as we have found, this is quite much computationally intensive. So actually this in order to calculate this inner part, we have to perform this potential-wise integration, and this potential-wise integration should be done for every electron quasi-Fermi potential value, which is divided into given voltage range. What was the range for this electron quasi-Fermi potential? The range was starting from our source voltage and ending at our drain voltage. If we apply, for example, 0.5 volt to our drain and source is grounded, then the voltage should vary from 0 to 0.5, and this area should be divided into several pieces for our V. So we have to calculate 0, 0.1, 0.2, and for each electron quasi-Fermi potential, we have to do this inner integral. So that is quite cumbersome, and yes, that was difficulty of PAUSA integral. So today we will try to evaluate even further simplified form of drain current expression. So maybe you can ask me that question. Well, in our microelectronics course, we have already studied the complete, quite seemingly good IV characteristics. Maybe you remember the formulation. So Cox mobility, effective mobility, W over L, and BGS something. And then why do we bother being bothered by this introducing this formulation once again? It is because the one we have studied in the microelectronics course is somewhat simplified version of more elaborated and more complete expression we will see from now on. Okay, so we are now studying the whole derivation procedure for accurate drain current. And another question is, well, why we are just concentrating on ID? That is quite easy, because in the case of DC, ID is almost equal to IS, source current, and there is almost no gate current, and substrate current or body current is really marginal, and the amplitude, magnitude is quite low. So that's the reason why we are currently concentrating on drain current only. Okay. So I think that is the motivation of today's lecture. Okay. So we are now introducing so-called charge sheet approximation. Charge sheet model is, in order to understand the necessity of this charge sheet model, first of all, we have to understand difficulty of this integration, inner integration. Inside, we had to perform this quite complicated integration for potential, and main motivation to perform this quite complicated integration was to calculate inversion charge density accurately. So if we have an alternative way to calculate inversion charge, then maybe we can skip this integral. That is the main motivation. And what we have done exactly is, we know quite well about QS. This is known, and this is decomposed into QI plus QD. So if we can introduce a certain approximation, good enough approximation for depletion charge density, then we know it, and we have good approximation for QD, then we can find also good approximated expression for QI, inversion charge density. This is the main motivation. So are you with me? Since the mobile charges are only the one contributing to current, calculation of this QI is quite an important task. And previously, in the case of PAUSA double integral, we did it quite rigorously. But we are now doing that in an approximate way. Then now you understand this key point. Simpler way is QD is approximated with this depletion charge approximation. So you know, this is just a square root dependence on the surface potential. So this is depletion charge approximation. So now we can write down in this way. Of course, this is exact, and QS can be well expressed as, once again, this expression. This relation is also exact. The only approximation is introduced by this part. So by approximating this shape of our depletion charge, or amount of depletion charge by this square root dependence, we can get approximate value. So where do we have similarity, not exact equity? So here we have this approximation. Of course, please note that it's not exact. But you know, we have already introduced several approximations to derive our equations. So I think that being exact or being a little bit approximated, that doesn't make a big deal to us. But point is how good an approximation is. So let's go to our numerical example. So currently we are talking about a certain device taken from 90 nanometer technology. So thickness, oxide thickness is 1.2 nanometer, equivalent to 1, and also Na equal to 10 to the 18 per cubic centimeter, and certain flat band voltage number. For that one, I just try to calculate two different method. Following two different ways, I try to calculate inversion charge density. This is corresponding to Qi. So of course, please be careful. When I say Qi, actually this is charge density. So if we are really rigorous, then I have to write down Coulomb per square centimeter. So per unit area, how much charge can be found. That is the way. However, sometimes it is well expressed as just number density, because everybody understand in our calculation there is minus q is related. So that's the reason why here I just to write down integrate the electron density instead of qi. So if we multiply minus q to this integrated electron density, then we can get charge per square centimeter. So we can easily get this conversion. And please note that the number, the numeric number, its order is 10 to the 13 per square centimeter. If we consider the quantity like 10 to the so in the unit of volume density per cubic centimeter, the numbers we are currently looking at is 10 to the 17, 18, 19, 20, 21. This is the number for our volume density. However, when we integrate it over vertical direction, since inversion layer is confined in a very short range, so our numeric number has a much lower density. When we have 10 to the 13 per cubic centimeter, you have to feel that this is quite a high density. 10 to the 13 is certainly very high density. 10 to the 12, yes, this is once again high density. If we go down to 10 to the 11, well, this is a moderate one. 10 to the 10, then we can say that this is certainly low density. And if we go to further and further down to 10 to the 9, 10 to the 8, then certainly we can say that this is there is almost no electron in our current conduction. So please note that in my feeling, 10 to the 12, that can be regarded as some borderline between strong inversion and relatively low inversion charge density. Okay, so certainly this is 1.5 times 10 to the 13 per cubic per square centimeter. This one shows quite strong inversion here, and this is corresponding to V equal to 0. And where is it? This is corresponding to y equal to 0, because we have assumed that we apply 0 voltage to our drain path. And you can find that here, once again, 0.5. What is it? In this case, I applied 0.5 to our drain, and this is corresponding to y equal to L. This is the drain end of our channel. Okay. Then please have a look at Q or inversion charge density calculated from Pausa expression here. So blue one is a Pausa, and here charge density charge density is calculated with the charge sheet approximation. So I just introduced the QD follows this square root of surface potential. Then by calculating in that way, you can find that the agreement is quite good. Then if we just draw the error, I think that this is the error. I calculated in that way. The difference between these two, pausa and charge sheet, divided by pausa relation. Then this is written in percent, and level is just about 1%. So 1% difference. Are you happy or unhappy to further improve this calculation? So actually in this case, since we have so many other approximation already introduced this derivation procedure, so in my opinion, actually the agreement between this pausa and charge sheet in this case is quite good. About 1% is really acceptable. But please be careful. In this case, I have used the exact phi sub s. So how can you calculate phi sub s? This is also a matter of our calculation. We have to spend our computational resources to calculate surface potential. But I just assume that anyhow we can calculate the exact phi s. Then by using that exact number into this depletion part, then we can get quite a good agreement between inversion charge density calculated by two different methods. Okay, so the feeling is, well, if we should be really rigorous, we have to perform this integral to calculate q sub I. However, if we adopt depletion charge approximation, then we can also have quite a good approximate expression for our q sub I. That was our feeling about this number, this situation. So now, instead of a previous expression, we had to perform integration over d phi. But once we know only surface potential, please note that previously, in order to calculate the q sub I, we had to know vertical profile of phi of x. However, now we are allowed just to calculate surface potential with only this one single number. We can calculate this q sub I approximately. So we are doing certain approximation, and we have the reduction of integration from double integral to just single integral. So now you can see that this is the expression. Previously we wanted to calculate q sub I by performing d phi integral. Now we can say, yeah, this is just one single number. So now here we introduce this number. So since qi is now written as a function of q sub I, now we have to make a certain variable conversion from here to, from our electron quasi-Fermi potential to the surface potential. That's the reason why previously our integration lower bound and upper bound were 0 and BD, but now we have to find out the surface potential and source side and surface potential at drain side. How can you calculate these two numbers? These two numbers can be calculated by slab-wise manner. So let's say this is the system, the MOSFET system, and currently we are just talking about the central part, intrinsic part. This is the domain we are currently considering. This is y equal to 0, and this is y equal to L. And for calculation of these two quantities, we have to perform this one-dimensional Poisson equation solution and one-dimensional Poisson equation solution for y equal to 0 and y equal to n. You can do it by solving the related equation for slab-wise. So from this one, you can calculate surface potential at source side, and you can calculate surface potential at drain side. With these two numbers, you can set upper bound and lower bound, and now integration of this integrand is required. Well, when you have a look at this qi as a function of phi sub s, then it is relatively simple. Oh, that is quite much relief to us. Please have a look at q sub I, although written in a quite previously written in a quite complicated manner, but when you have a look at this equation, in terms of our surface potential, it is extremely simple expression. The first one is constant term, because this is nothing related with the surface potential, and there is a linear term. This is minus Cox, so minus is gone, and Cox phi sub s, so this is just linear. You can easily integrate it. And finally, here you have the term related to the diffusion charge, and this is just square root of our surface potential. So simply speaking, so although it seems like QS is written in a complicated form, but I can say that this is constant plus phi s plus square root of phi s. That's it. That's it for q sub I. So it means that if our the term originated from our variable change is simple enough, then this integration can be calculated quite easily. Okay, so you know this one, once again, constant and linear and square root. That's it. So if this one is just a constant, well, we will be very happy. But if this is not a constant, then we have to find a little bit further elaboration. But anyhow, the situation is not that bad. We can do it. Okay. So now let's come back to the initial question by our students. So one student asked me, what is the relation between electron quadriform potential and electrostatic potential? So everywhere inside this system, of course, let me just do it more rigorously. Everywhere inside our system, we can define several quantities, and one of them is electron quadriform potential, and of course we can also introduce electrostatic potential. Then from these two numbers, we can also calculate electron density at that given position by intrinsic carrier density and phi minus phi n and kBt over q. That can be calculated at every position inside our two-dimensional cross section. But currently we are not talking about these numbers. There are several approximations to make it into surface potential and V numbers. Our assumption was, okay, along this direction, we will have the same electron quadriform potential. If we, for example, if there is 0.1 volt for our quasi-Fermi potential and say that this is 0.0 volt for quasi-Fermi potential, then what will happen? If phi n equal to 0.1, phi n equal to 0.0, it means that there is a gradient of our electron quasi-Fermi potential, and current density is proportional to the gradient of electron quasi-Fermi potential. So it means that we have to have electron flux. It means that if we allow any meaningful difference of our electron quasi-Fermi potential along this vertical direction, it is directly corresponding to the vertical current conduction, which is obviously contradictory to this to the operation of our MOSFET. That's the reason why we can introduce a slab-wise uniform electron quasi-Fermi potential, and that was written as phi v sub y. And here also we have electrostatic potential, and we following Professor Tower's notation, instead of this quantity, we introduce a certain quantity biased to minus phi x equal to infinity for given y position. That was assumed in our previous calculation, and this is shared for all different y values, and this is in our case written as potential. So that was our previous simplification procedure to get phi and v, and we have different values. So if we follow this notation, then in deep substrate, of course phi will be 0, and if we go to this part, we will have a certain value corresponding to the band bending, actually minus q band bending divided by minus q, and this quantity is here written as surface potential. So please note that the range of our variables, in the case of our electron quasi-Fermi potential, within this system, the minimum value we can imagine in this system for electron quasi-Fermi potential is source voltage. Source voltage is the minimum value we can imagine for this electron quasi-Fermi potential. Then what is the maximum one? The maximum one is drain voltage. So electron quasi-Fermi potential varies from, simply speaking, 0 to 0.5, 0 to 1.1 volt. This is the range of varying electron quasi-Fermi potential. And please think about the range of our phi or surface potential in following Professor Tower's notation. Then in order to get our inversion characteristics, this should be about 2 times phi b. You know what is phi b. So simply speaking, surface potential and electron quasi-Fermi potential inside this notation cannot have similar numeric values. They have, from their starting point, they have quite much separation. So their range is about from 0 to something, and its variation is related with around 2 times phi b when we consider certain operation, normal operation condition. So they are quite much different. Yes, I hope that all of you understand this point already quite well. Then the next question is, yes, we know these two quantities are different. Well, however, if we have just a simple relation like this. Then although they have an offset between V and surface potential, but they can be regarded as the same quantity. So just to shift it. But actually it's not. This is not true always. And let's have a look at what really happens to these two quantities. So let's have a look at this one. Well, since our goal is to calculate dV over d phi s, then first of all we have to find out the functional form of V in terms of phi sub s surface potential. After that we can make the first order derivative. So by this is corresponding to a simplified version of Amor's equation. Why I'm saying simplified version? So here actually we have to have 6 different terms, but there I neglected some unimportant terms and take only 2 important terms. This one is corresponding to the QD related one, and this one is related to the electron related contribution, and they are coupled by sum, and overall integration should be taken. So anyway, by starting from this a little bit approximated form for our electron quadriform potential and surface potential here and there, then we can get, so I will skip the derivation procedure, or we can get the expression of electron quadriform potential in terms of surface potential. It looks quite complicated. Well, so please come back. Our here I just wrote in that way. Our naive assumption is, okay, how about this one? If we have the linear relationship between quadriform potential and surface potential, then we will be very happy. But in reality, from this MOS equation, we can find that actually V is equal to surface potential. Yes, that is corresponding to V equal to phi s. However, this second additional term has relatively complicated expression. So also, unfortunately, this is a function of phi sub s. So we do not expect that this is a real constant. Of course, whether that is literally constant or some variation is small enough, we have to find it. But anyhow, its functional form looks quite complicated. Okay. Then let's have a look at this one. I think that this graph is quite important. If you have a look at Professor Tower's book, the second edition, you can find a similar but not identical figure in figure 3.3. The x and y axes are exchanged, but you can find similar information there. So here I consider 3 different gate voltages: 0.3, 0.7, and 1.1, and we are currently trying to understand the relationship between electron quadriform potential and surface potential, and this graph exactly shows that quantity. Here we have V, here we have surface potential. Then how does it look like? If you look those graphs carefully, then you will find this number, this trend. Starting from here, the distance is 0.2, and this distance is 0.2. although aspect ratio is not exactly 1:1, but you can understand the diagonal line shown here, that is corresponding to the linearity. If it follows this slope here, then it is corresponding to V just to increase when surface potential increase exactly. Then how does it look like? So when you have a look at this green curve corresponding to 1.1 volt, then it really follows similar graphs. And wow, good. However, so at a certain point, suddenly this relation deviates, and we have quite a strange behavior. Rapid increase of electron quadriform potential. So actually, as shown in Professor Tower's figure, the more natural way is to draw the surface potential as a function of electron quadriform potential. Please also have a look at the figure by Professor Tower. But anyway, you can understand at least the linearity for some reasons holds. However, also there is a strong deviation from that linear relation. So we have to understand, for some cases, when we increase electron quadriform potential, then surface potential is also increased accordingly. That is the usual case. But for some cases, it's not. Okay. So think about this one. So let me try to give you qualitative understanding on this behavior. I assume that all of you quite well understand the behavior of our MOS system when it is just biased to zero electron quadriform potential. Then what we have done was, for given gate voltage, so what we have found from this system is, when we have a certain positive gate voltage, and when it is when substrate is grounded, so voltage quadriform potential is 0, then we want to supply negative charge in this substrate, and we have two different ways, as repeated again and again. One is depletion and one is inversion, and you know that they have different sensitivity to the surface potential. This one has a quite slow dependence on surface potential, as we have assumed in square root dependency, and this guy has quite exponentially dependent on the surface potential. So roughly speaking, we can write down in this way. So that's the reason why always first depletion takes the control. After that, when the surface potential gets a certain value, then now this one becomes quite strong. So later this one becomes inversion charge is the dominant way to provide negative charge. That was the situation. Then I hope that all of you understand this one. Then now let's just increase it to a certain voltage, 0.1 volt additionally. Then please think about the relative strength of these two mechanisms. What happens? QD, is it related? Its functional form is related to the this phi. It doesn't have any dependency on V explicitly. So its ability is more or less given. Then now let's have a look at this Q sub I part, inversion charge. It is really directly affected by what? Affected by this change of electron quadriformy potential. So if we introduce this positive electron quadriformy potential, actually previous ability to dominant the negative charge supply is now lost. So for example, if we apply just 1.1 volt to this system, then actually there is no way for this guy to supply negative inversion charge to the same amount, because we have to consider the quantity like 1 volt, exponential something, and 1 volt, and this one becomes ineffective. Well, now we understand if we apply so drastic V value, then this one becomes quite much ineffective, and all kinds of our potential variation should be, or negative charge should be provided by this depletion charge. But that is the case of really high voltage. Instead, think about this one. If we apply just 1 millivolt, then what will happen? Then now we will have a slight decrease of this capability to generate inversion charge, and by slightly increase our surface potential by same amount, 1 millivolt, then we can still keep the same amount of negative inversion charge, and by increasing this 1 millivolt, actually the depletion charge does not change much. So in this case, so let me just summarize. So let's say that here we have a certain given V value, and now we introduce V plus a little bit changed delta V value. Then if we have this case, then if our inversion charge still effective to provide negative charge, then our surface charge will also change the same amount. By just following this change of electron quadriform potential, then we will have actually this behavior, Qs minus V, but their increase delta V and their decrease delta V, they are cancelled out, and we will have the same contribution from negative inversion charge. And this small change will also introduce change of our negative charge density or due to the depletion charge, but that doesn't make a big deal for our depletion charge. That is usual case when we have sufficient ability to get inversion charge. Simply speaking, if we are in the strong inversion region, then this is the case. However, if this becomes ineffective one, so although we have certain changes, it doesn't make any difference, then we cannot make this kind of thing any further. So simply speaking, the behavior between electron quadriformy potential and surface potential is sometimes, for strong region, they are one-to-one, they have the one-to-one relation. But when we go to relatively lowly biased gate bias condition, or sometimes the bias where we have quite a high drain voltage, then we found that this ability is gone, and now we have a much different behavior. So since now we understand V of phi sub S, then the remaining part is just manipulation. But I strongly recommend you to do it by yourself, because there are so many numbers, and this from this one that one, or from this one to the next part, this is not directly done, and we have make some cleaning for some coefficient. Number 2 is going to there and there, and signs are positive, negative, and rearranged. So please do it once again by yourself. So this is quite important. And doing it by yourself is important, but anyway, since this is just an analytic expression, so finally we will get this final expression, 1 plus something. So now that's the reason why here we have 1 and something, and the one we have shown here is corresponding to this 1 and something. The slope 1 is corresponding to this the first term, and second term is corresponding to this very high steep part is corresponding to the second part, and this is, we can feel that this term or this behavior is important when we go to high drain bias or the position close to the drain end. Then we will have a quite a high electron quadriforming potential, and that part we will have this kind of behavior. Okay, well, now next task is just to put this expression into our previous one. Then please guess what will happen. Here, this is dV over d phi s, and our Qi have 3 different terms: constant term, and linear term, and square root term. So see what will happen. Multiplying it by 1, so that will generate quite an easy one. But when you multiply this Qi expression and this quite a complicated one, well, it's not that easy to do the real calculation. So this is done here. When you have done it here we have Q sub I. As I told you, once again, this one has a constant term, and also phi s and square root of phi s. So it's okay to evaluate the integration, but the second term have, well, so a little bit complicated term. So how can we calculate? So in the charge sheet model, instead of evaluating this one exactly, we wanted to introduce a further simplification. So this is one. Here I just to show you once again the numerical example. Now our integrand have 2 different parts. The first part is minus Qi, and second term is quite complicated term, which is important when the drain voltage is high. Then this solid line is corresponding to minus Qi term, and here we have a dashed line corresponding to the second term, and of course this is a surface potential phi sub s, and by integrating these graphs two curves, this one and that one, we can get the integral result, and that is corresponding to the ID. So please try to estimate the relative contribution to our case. For example, if we integrate this first one, qi term minus qi term, then we will have this area contributed from the first term minus qi. Then now let's estimate contribution from second term. How large is it? This is corresponding to integration of this number. So as you know, if we draw, let me just draw once again quite schematically. So simply speaking, it looks like this, and here we have, yes, this one is a contribution from second term, and this one is contribution from the first term. So for gate voltage equal to 1.1 volt, we can certainly say that the first term is really dominant. Even we can neglect the second term. Well, that doesn't matter. But please have a look at the result for gate voltage equal to 0.3 volt. Then when you have a look at this one, how does it look like? If we consider the integration, then you will find that this is the contribution from the first term, and second term's contribution is no longer negligible when you have a look at these two numbers. So that's the problem. If we are talking about just cases for 1.1 volt, we will be quite happy because the second term is complicated and we can just kick it out because its area underlying the curve is not that large, so we can just evaluate only the first term. But the reality is, if we go to lower and lower gate bias voltage, then this one really makes certain contribution. So as you can see here, even the contribution from the second term is almost gate bias independent. So this curve here, you can find that green dashed line, and you can see here yellow dashed line, and here you can see blue dashed line, and all over three graphs almost overlapped. Means that regardless value of your applied gate bias, the second term contribute. And please have a look at this one. This is really related to the or dependent on the gate voltage. If you apply high gate bias, then this solid line QI related terms goes up and readily becoming the dominant term. So the problem is now this second term is related with moderate inversion. I mean that. So not inversion charge is not overwhelmingly dominant to all over other contribution. When that happens, then actually we have to consider this second term. Well, so the point is we cannot kick out the second term completely. Anyhow, we should consider second term. How can we do that? That is the key consideration, and the consideration comes from this one. Point is, well, it is almost a flat line. No, this is really flat line. So point is, instead of actually calculate this second term as a function of phi, select a representative value of surface potential and evaluate that second term and use that simplified form to take integration. That is the main trick to make a simplification. So applying this condition, so how can you have this one? This is nothing but this left hand side term is qs and this right hand side term is qi. Qs, substrate charge, is almost completely given by q sub d. What does it mean? There is almost no inversion charge. That is the assumption we are currently applying. Using that expression, please, it's not that obvious the conversion from this expression to the second next one. Please have a look at this quite complicated one, and this part is actually just replaced by this term, because we are now saying that they are comparable in most cases. So now we have a much simplified form. Please be careful. There are many different ways to make a certain simplification, and this is one way to do that. And by applying that one, we will get relatively simplified form for this second term. Once again, please have a look at this one. This one have the form of, here lower part we have a square root of phi, and here we have also square root of phi plus a certain constant. So this first term can be regarded as just a constant, and this second term now can be regarded as qs minus half power. So also it can be integrated analytically. So now by doing this assumption, finally we have the expression for drain current. So now please try to find out contribution from each component. Here we have Cox VGS minus flat band times phi s. This is originated from our Qi expression. And also here we have another one. This is also related to our Qi expression. And this guy is originated from our previous square root phi sub s. All of these terms are coming from our just Qi integration. However, we have other terms like this is corresponding to a constant, and this one is corresponding to over phi s minus half power, and each of them contribute this wavy and another wavy terms. Okay, so now you can understand, by considering that much complicated second term, we can introduce a little modification for our drain current expression. But anyway, we will have this form. Then how can you actually calculate this drain current expression? Please note that there is no longer existing any kind of integration. No, you don't have to perform any kind of integration. what you can do is just to evaluate this upper bound and lower bound of your expression, your surface potential, and get these two numbers and just insert here, there, and there for your drain end surface potential and source end surface potential. By taking their differences, evaluate this expression twice and taking the difference. That is enough to calculate this entire drain current expression. Well, when we compare ourselves, well, please try to remember our previous Pausa integral. In order to calculate Pausa integral, for every slab, every electron quasi-Fermi potential, you have to solve MOS equation and also integrate that result along our electron quasi-Fermi potential. That was a quite complicated Pausa double integral. But now, what we can do is just to solve MOS equation only twice. Why twice? Calculate this drain end surface potential and source end surface potential. After that, yes, that's it. Just to insert these two boundary values or bound values, upper bound and lower bound, then evaluate it and take the difference. That is enough to calculate our drain current. Much more simplified than the original Pausa equation. Of course, you can ask me this question. Well, in order to make such kind of a quite simplified expression, we have introduced many approximations. What was it? The first one was charge approximation. We introduced depletion approximation for our depletion charge, and from that one we make an approximate expression for inversion charge. And another one was, yes, please have a look at this. Now here we have introduced by changing the variable, we can find a quite complicated form for the dependency between electron quasi-Fermi potential and surface potential. And after that, this second term is anyhow approximated. And the main trick of approximation was introduce an alternative form for our electrostatic potential. What was it? That was just this expression. Almost no inversion charge is existing when we fix this surface potential. Of course, if we go to the case where this is not the case, if we have Qi is much higher than 0, then obviously this relation is not that accurate, where we can expect the failure of this behavior. For example, in the case of a gate voltage equal to 1.1, we expect that this expression is quite good for this range. However, if we go to lower and lower surface potential, that will be quite inaccurate. But that doesn't matter, because anyhow the behavior of our expression is our second term is not that high, so that is justification. So I'm not saying that this is exact, but this is a quite much acceptable approximation for treating the second term. So that's the way we finally get this quite simplified drain terminal current. You find that still this is not for a function of our drain bias and source bias. You know, this expression is already quite simplified, but in order to calculate the drain current, first of all, we have to calculate phi SD and phi SS starting from the given quasi-Fermi potential. Still, that is complicated. And in our microelectronics course, we have already studied certain triode region expression and also saturation region expression. Then how can we relate this more valid and rigorous one and region-wise expression? So that will be covered in our next lecture, the last lecture before the midterm examination. And our midterm examination will cover the entire lecture contents up to lecture 13. Okay, so I think that's it for today's lecture. And if you have any question, then please come to me after this session is over. Thank you.